Hey folks, we're back with another solution video for one of our instructional problems. This one's number 49 from chapter 10. A horizontal spring with spring constant of 100 newtons per meter is compressed 20 centimeters and used to launch a 2.5 kilogram box across a frictionless horizontal surface. After the box travels some distance, the surface becomes rough. The coefficient of kinetic friction of the box on the surface is 0.15. So our first task is to draw a picture of the scenario to the right of the prompt, just like in the last instructional problem. It doesn't need to be anything fancy, but this is all a horizontal surface here, so it's nice and easy. We can draw just a spring and a box. Let's make a slightly nicer box there. There we go. And then we know that we've displaced this some amount. We've displaced this, I believe it's 20 centimeters. We'll have to change that to meters in a second. Our K value is 100 newtons per meter. We know that this is a 2.5 kilogram box. And then some distance later, we have some friction. Maybe let's do a different color or something. I have some friction here, and it continues on, and we're saying that the coefficient of kinetic friction here is 0.15. So I think this is probably good enough to get started here. It's simple, it's basic, but it kind of clues us into what's going on. What's interesting is we're not told how far this distance is. We're not actually given how far the box moves until we get to the friction-filled area. Let's see if that becomes a problem for us. Maybe it will, maybe it won't. Is this an isolated or non-isolated system? Explain. Well, I think this open-ended kind of question can be argued for both. I think that you could argue that it's an isolated system for a portion of it, right? I think that this frictionless spring-loaded system is isolated. There's no interaction, no work being done by the environment. I think, though, if we looked at the entire thing, we would have to include the non-isolated, I can't spell today, isolated region of the friction on this area. So I think it has sections of both. I think if we were to look at the entire system, I would maybe say, non-isolated, simply due to the friction portion of the problem. I'll say ramp here. The rest is isolated. So again, we consider an isolated system when I have no work done by the environment on my system. Specifically non-conservative forces like friction or applied forces or things like that. It's non-isolated when there is friction and applied forces. Then I need to consider the work externally done. All right, part C, how much elastic spring potential energy is present in the system initially? How much is present at the end? So initially, we have some compression of 20 centimeters here. So we can write out our, not K, we're going to write out UE is equal to 1/2 K xi squared, where xi is the displacement, the initial displacement from equilibrium of our spring. So I have 1/2 100 newtons per meter here. Times my displacement of 0.2 meters quantity squared. Right? If I were to plug that into a calculator, 0.5 times 100 times 0.2 times 0.2 gives me 2. joules. We've stored 2 joules of energy in this spring scenario, in this spring system. How much is present at the end? How much energy is present down here? Well, we've extended our spring system, we've decompressed it, and if we've decompressed it completely, that means that there are no other forces on that spring or from that spring. And so I'm not going to decompress or compress, I'm not going to stretch it or compress it any further. When my box is all the way out there, I have an elastic potential energy of 0. Because my spring has relaxed completely and is back now to its equilibrium length. So the displacement from equilibrium, xf, if we think about that, is 0. The other thing I want to mention here is that our box is not attached to the spring. It's simply held up against the spring initially. So when you actually get to the equilibrium length, the box detaches. It stops being connected to the spring, and so the box is not going to pull the spring or anything like that. All right, so part D, how much kinetic energy is there initially in the system? How much is there at the end? Initially, we're not moving, right? Initially, we have compressed this spring and we're ready to let go and let it fly, so there's no movement. Kinetic energy initially is equal to 0. Our second part at the end, right? At the end, well, if it's becoming rough, if the problem states that this path becomes rough with some friction, I'm probably going to start slowing down. If I'm slowing down all the way at the end, I will have a kinetic energy of 0 as well. Right? I'll have some non-zero kinetic energy all the way in between these 2 endpoints, but if I look at the very initial portion and the eventual end when I've come to rest, then I'm going to have no kinetic energy in either of these scenarios. So then, how much does the gravitational potential change in the system from beginning to end? The big thing here is that we are told this entire surface is horizontal. Even the friction-filled area, right? It's horizontal. So if it's horizontal, h never changes. My height, my altitude never changes. And so if I think about mgh, right, the delta of that, right, let's say mg delta h would be 0, right? This is our delta ug. I'm at the same gravitational potential energy the entire time. So I don't know how much that is. We always make it relative to something. I think it would make sense to say right on the surface that we're on, we would say ug equals 0 at that point, and any deviation from the height of that surface would give me some potential energy or take some away. But in this case, we never deviate from that surface. I would say the entire thing is just held at 0. So how much work must friction do on the box to stop it? Well, the initial part of our system here, so if we think back to part B here, if we think back to part B, we're saying that a non-isolated system, delta E, our total mechanical change in energy, is equal to the work externally done, right? How much work must friction do on the box? Well, that is this external work. So if I break this apart a little bit, I have the change in kinetic energy, I have the change in gravitational potential energy, and I have the change in spring potential energy or elastic potential energy. This has to be equal to the work done by the system. So if I start and end with 0 kinetic energy and I have 0 change in gravitational energy, and I go back to part C, how much elastic potential energy is there, right? What's the change in that? It's final minus initial, so 0 minus 2 joules is my change in elastic potential energy. That has to be equal to the work externally done by friction. So the work totally done by friction, the work done by friction to stop this box, is negative 2 joules of work. Lastly, from our definition of work, how far does the box move along the rough surface? So that's what's interesting about when we consider energy. If there's no external work being done by the environment, it does not matter how far of a distance is in between this, starting point of the block and the friction filled area. I don't care because there's no friction there, there's no change in kinetic energy. It's as if it's as close or as far away as we need it to be. So the only place that displacement actually matters here is along the rough surface. If I think about my work done, I have some force dotted with some displacement if and only if this force is constant. If we think about friction force, though, as long as I'm not changing my normal force, right, friction force is always equal to Fn times mu k when I'm thinking about kinetic friction. So Fn is not changing. I am horizontal this entire way through, and so if I'm horizontal, right, my mg equals my Fn. I can say that my work then is equal to mg mu k times this delta x, and we said in the last part, in part F, that the total work done by friction had to be equal to negative 2 joules. Where'd that negative come from? I think I got a little bit of ahead of myself here. I missed something, right? I missed this dot product. This dot product's really important. This dot product gives us a cosine of an angle between my friction force and my displacement, right? If I think about this, I'm displacing to the right, as I've defined it, and my friction force then is going to move, or going to point to the left. And so I actually have a cosine of 180 degrees in here that I forgot to write, and this is going to be the negative. It cancels with this negative, giving us a positive displacement. So last thing, we need to plug some numbers in. I have 2.5 kilograms times 9.8 meters per second squared times, what did we say? It was 0.15 for my coefficient of kinetic friction, and then I have delta x here that I don't know. Let's throw a negative sign out here, equals negative 2 joules. If I solve for delta x, right, negative negative is going to cancel. 2 divided by a quantity of 2.5 times 9.8 times 0.15 should give me delta x equal to 0.54 meters. So that's this problem. I'm going to slide 0.54 meters along this friction-filled area. The reason we asked all these intermediate questions is to really kind of build up a process on how to approach part F here and part G. We're saying that, the change in these energies, if I just look at the beginning and the end of the problem, is 0 in a lot of these cases, and that really simplifies the problem, because anything I put into our system has to be what I take out, or what I'm left with, right? Elastic potential energy was the only thing that we put into the system, right? Friction's taking it out. Everything, I convert from elastic to kinetic, and then take that out from friction, the work done by friction. But that conversion from elastic to kinetic is actually not necessary. It's not necessary to dive into to solve this problem. So that's this last tutorial problem, this last instructional problem. If you have any questions, feel free to email me or swing into an office hour. Have a good one.